Hi, I'm Dan Francis, and welcome back to the Weekly Buffer. Today we'll be in production taking a look at the Sentinel Clock assembly. I want to walk you through the different steps it takes to build this assembly and all the components that make up the Sentinel Clock. Trisha, our technician, will be doing the assembly work today, and I will narrate some of the steps and components that go into the assembly and explain what their function is and how they add to the performance of the Sentinel Clock. I will also have a brief overview of the clock topology and show a complete Sentinel Clock system in its entirety. Here we're adding gap pad into the bottom chassis. This gap pad will heat sink devices on the clock boards themselves. These pieces of aluminum are alloydined for electrical connectivity. So it looks like raw aluminum, but is in fact plated with this finish to allow good electrical connections between these EMI gaskets and the PCBs themselves. Now the whole enclosure is EMI protected, but the very sensitive electronics of the clock oscillators have a secondary EMI enclosure. So these gaskets being installed now are on the bottom of the circuit board. So it will be sandwiching the PCBs in the casework. And you can see there's two chambers to this EMI. One is where the crystal is oscillating, and one is the driver circuitry. These EMI gaskets are a relatively hard rubber that have very sharp particles in them that help them bite into the allodyne finish. And then they'll be pressed up against the gold-plated circuit boards. And as this compresses, it'll press on that EMI gasket, making a firm connection between the casework and the PCB. This looks like a duplicate of the circuit board, but these are slightly different to drive the different crystal frequencies. So we have one dedicated for the 44.1 and its family, and then one dedicated for 48K and its family of frequencies. Each of these PCBs is already pre-tested with known clock crystals, but we can't actually measure the performance of them until they're fully encased with EMI protection and isolation. On the PCBs, we've also conformal coated the finish, so this helps protect all of the solder joints and circuitry from any kind of air exposure. So now installing the cover. So we'll start with putting the hardware in corner to corner for alignment. As we tighten the hardware, we're going to start compressing that EMI gasket, making a very good connection to the PCB. We use torque drivers for all the hardware on the Sentinel DAC. This ensures a consistent assembly. The clock itself is isolated mechanically from the rest of the case with wire springs, but because of shipping drops and movement, we have to install rubber stop to help with any potential shipping movement. So these here are bumpers for the compression. We considered having the clock locked into place for shipping and then requiring the unit to be opened and have stops removed, but we were able to come up with a design that was able to protect it and keep it safe for shipping and then be ready to use upon arrival. Here we're adding the lock washers and then the nuts for the clock signal connectors. These gold-plated nuts and washers make a great connection to the allodyne case as they are in the EMI section of the clock. Now these are gently tightened as it's just an electrical connection and not required for mechanical strength. So here we are installing our custom wire rope isolators. These are ultra fine fibers that dissipate energy from movement, and you can see that they're not symmetrical on the chassis itself because each of them is tuned to hold the same amount of weight. So we found the center of mass of the clock by first building the unit completely and then measuring the actual values so that these can be located around that mass so that when it's fully loaded, there is an equal balance on each isolator. This is a really hard technology to use in our industry because you can't adjust the load-bearing weight easily. So if you wanted to use these for, say, a product shelf or product feet, you would have to tune each one precisely. It would make it impossible to sell as a universal product. So as we add the isolation base, you'll notice that the mounting points for these springs are further apart than they are on the clock itself. This is because we're preloading the springs so that the clock wants to remain centered. These are Delrin springs that are only used in the event of shipping. They help absorb the energy from the clock moving. These provide the maximum limits of movement and protect the springs from being overstressed. Here we are installing the EMI gasket for each of the crystal ovens. After the assembly is complete, each clock has its own carrier tray that it uses to move through production to keep it safe and protected. This allows the clock to be measured while being able to freely move on its isolation pads and then stored for safekeeping. Each crystal has its own copper case that it's mounted to. This is the oven mechanism that we use to regulate the temperature. The thermal mass of the copper helps keep a consistent temperature as it's used. You can see here on the bottom, the crystal is installed with these gold pogo pins. So when we install this into each clock, those pins press on pads to make the connection. This allows us to create and test these small sub-assemblies. Now, before the crystal is installed, we will be installing them into their own oven cases. So these are Aladyne cases that are going to be used to keep the EMI barrier in place. So we will be using a foam to insulate the crystal here. So after installed in the case, this will become a crystal assembly that we can then use and plug into the Sentinel clock. So in many cases, they'll use a 10 megahertz clock like this, and then split the frequency between two sample rates for the two sample rate families. You can step that up even further by using two clocks, one for each sample rate. But what we've done here at MSB is we've built the clock from the ground up. So this here is equivalent to this here. In most products, you're going to see this standard clock surrounded by electronics like power supplies to drive it. In an external clock, it'll be one or two of these on a circuit board with power supplies. So this adds a lot of phase noise having it separate from the rest of the unit. So starting with the Femto X in the Sentinel DAC, we have our two sample rates, the 24 and 22 megahertz crystals. So what do we have to drive these? Here is the clock distribution. This here is an EMI cage on the main distribution board that separates the incoming signals from the clock and sends them to the right and left mono DACs. This is also where our clock power comes from. You'll see power supply filtering, and below another circuit board for more power supply filtering. This here has connections to the clock for power and signal. From here, we go through the Sentinel umbilical cables to the power supply, and this here is the clock power supply. The clock then has two dedicated transformers, and last, it has the AC input and power filtering. So this here is the complete femto clock for the Sentinel DAC. The complete system of the Sentinel clock starts with the AC input, then goes to two dedicated transformers for the clock, then goes to the power regulation and power supply for the clock, this dedicated board. It then goes through the umbilical cables to the clock power distribution. It then travels across cables to the Sentinel clock. The clock signal is generated and then comes back over coax cables. And then from here, it is distributed to the left and right mono DACs. I hope you enjoyed that look into the Sentinel Clock assembly. If you have any comments, please drop them down below, or like and subscribe to stay up to date with weekly videos from MSB. Thanks for joining us today, and we'll see you in the next one.